Alright, hello, math fans and video watchers. Today we're gonna do a real interesting proof, and that is of Euler's identity, which is, you can see right here as follows. E to the I pi plus 1 is equal to 0. That's pretty cool that all those numbers are connected that way. And we could prove this, at least yeah, we could prove this with a Taylor series. So the three we gotta remember for this are the infinite series expansion of e to the x, or in this case z, is 1, well, you could see it here, but 1 plus z plus 1 over 2 factorial z squared, so on and so forth. Sine is as followed, you can see it right here, z minus 1 over 3 factorial times z to the third plus 1 over 5 factorial, z to the fifth, so on, and cosine of z you could see right here. And the reason we're using z is because we are going to substitute. So we could set z equal to I theta. And now we could plug this in to our infinite series of e to the I theta. So let's start with 1, it stays the same, plus I theta plus 1 over 2 squared times I theta squared, whole term, plus I over, or 1 over 3 factorial times I theta to the third, and so on and so forth. But what we gotta remember here is our powers of I. So just as a refresher, we'll do this in a different color. I to the first is I. I raised to the second is negative 1. I raised to the third is negative I. And I raised to the fourth is 1. So what's important here, as you can see here, is that these two, I to the first and I to the third, still have I in them. And these two, I to the second and I to the fourth, are no longer have I. It factors itself out. Now, knowing what we know about powers of I, we can could take this series and we could see here I squared. Well, why don't we simplify this term? It'll be negative 1 theta squared. So I is no longer part of that term. This will be negative I theta squared. Alright, so I's still here. And this one is just going to be theta to the fourth. So how about we do this? We are going to factor I out of all of the odd powers of I as to just have real numbers being multiplied by I. So we could see here, if I factor I out of every term that would still have I in it, it'll be theta minus 1 over 3 factorial times theta cubed plus 1 over 3 factorial times, or plus 1 over 5 factorial times theta to the fifth, so on. And if I leave all the values of this series in which I multiplies itself out of 1 minus 1 over 2 factorial times theta squared plus 1 over 4 factorial times theta to the fourth, so on, so forth. And what's interesting here, if you were paying attention before, you could see that this is just sine. While this infinite series right here, the one that I isn't part of, is cosine. So why don't we rewrite this as follows? E to the I theta is equal to I times sine of theta plus cosine of theta. And now that we know this, we can plug in pi. So why don't we try that? We'll set theta right here. Theta is equal to pi. So I times sine of pi, well, sine of pi is 0, so that'll cancel out. And cosine of pi is -1, so that'll be equal to -1. Now we could say that e to the I pi is equal to -1. If we add 1 to the other side, we get e to the I pi plus 1 is equal to 0. And this right here, this is Euler's identity. Alright, thank y'all for tuning in. Another math video. Probably have another dumb video game video going up. And after this, if you like math, stay tuned for the long-awaited video on curl and divergence. Thank you and good night.